Hello, everyone. My name is Alex. I'm a mechanical engineer, and I work for Schüco USA for the Virtual Construction Lab, and we specialize on research and development. Schüco is a company that has been around since the 1950s in Germany, and it makes windows and facades. And I have written this paper, the design for circular disassembly of high-performance facade systems, together with a co-worker, Naomi, but she cannot be here, unfortunately. So I will start. The construction industry faces urgent pressure to reduce emission, and extending the product life cycle is key. Current AC practice favors demolition over renovation, and it overlooks the energy cost of demolition and waste. Rapid tech advancements leads to faster facade system obsolescence, as currently systems have, for example, automatic mechanisms to open and close, and they have lithium, cobalt, and other dangerous substances that can pollute the environment if they end up in landfills. And entire facades are often replaced instead of upgraded due to design limitations, even though these systems are very expensive to manufacture in the first place. And deconstruction recovers materials, but requires system designed for disassembly. So today I will discuss about design for disassembly for facade systems, and I will focus specifically on the AWS 75 SI Plus system, which is one of the most popular systems that Schüco sells. So here you can see the current stages of the product, and what we want to do is, instead of having this sort of cycle, to transition to this one, which basically you go from instead of demolishing the building in stage C1, we deconstruct the building, and then after conducting quality inspection on some of the parts of the product, we reuse it. Because, of course, when a new product or a new part is manufactured, testing needs to be made either way. So the idea is that if the product is assembled and the parts are not corroded, they don't have such problems, but aluminum doesn't have these problems, it can be directly reused, saving material and lowering the GWP by extending the product life cycle. And despite available tools, facade disassembly is lacking, the research on it. And the current high-performance facades use non-circular adhesive and fixed connections. So when the systems are put together on the corners of the window, there are used some adhesives that they cannot be removed. And the problem with this is that then you have to basically send everything to recycle as a big piece with plastic and other components inside. And this is very difficult for sorting and recycling because it lowers the recycling by a lot. So design for disassembly can help with that. And we have developed this app that helps you give a score to how good your product is. And if you're a designer, it gives you also feedback on what you have to do better the next time you make the product. And this app, the nice thing is that it's not only for Windows, it can be used for a car or for a bicycle or for any product, because it's dependent on the data we input. And as I said, the goal is to reduce construction waste, promote material reuse, and advance circular economy practices in facades. As you can see here, this is a composite profile that has been tested and it has failed. And we can see here the permanent connection. So the aluminum is permanently connected to the thermal break. We need the thermal break because the plastic is not a good conductor of thermal energy. And if the profile was just aluminum, the heat would dissipate into the environment. So we put a thermal bridge, let's say, with a plastic so that it does not, the heat does not go in the building or the cold. And here is the permanent connection that is required to reach structural rigidity. But this connection hinders disassembly and reduces the recycling of the product. So this tool interfaces with an application called Schüco. Schüco is very popular. Whoever has heard of Schüco. It's this software. It's a desktop application that basically, if you want to buy a product, the sales representative shows you the configuration, and then you say, yes, that's a good configuration. I want to buy it. So this software that I have written with my colleague interfaces with the desktop app that is a legacy app. Let's say it exists for many years, and it extracts from the bill of materials useful information for the deconstruction report, as well as environmental product declaration information that this app can provide. And additional inputs are obtained from fabricators, because a lot of the times the fabricators add epoxy or sealants or no tricks that we don't know that we are developing the software. So we had to ask these fabricators what are the problems that they have. And there has been a combined data set that includes system type, material composition, component weight, disassembly action, required equipment, recovery potential, disassembly effort index, and a lot of other parameters. And this gives a deconstruction report that looks like that on the right for the whole product. And it lists, for example, that there are 23 reusable components, 37 recyclable components, and it gives the weight of the components. And this is how it works. More simplistically, there are three services. The first service calculates the ratio for the deconstruction score. The second one sequences the components and explains how long it takes for every sequence. So in order to disassemble a window, it takes, I don't know, half an hour, and there are 50, 60 steps. So you have to follow a specific sequence to do it as well as possible. And this service does that. And then the service C gives the material circularity index, the water circularity, and the energy circularity. And all this is given in a PDF report. And this methodology was applied as a case study to the AWS 75 SI Plus system. And the assembly process was reverse engineered, because currently at Schüco we do not deconstruct any windows yet. And these are the methodologies used and the different literature reviews that were done. And we said that the application outputs can be exported to PDF or integrated into Internet of Facades and material passports for broader stakeholder use. So as you mentioned before with the material passports, this could be in addition to an EPD. We could also have this deconstruction score that focuses on reuse and not necessarily on GWP today, but on the GWP in 30, 40 years later. So on the left, we have the scores for a window that does not open. So it's a fixed light window. And you can see how many components there are, the materials, the total number of reusable, recycle, and waste items. The material circularity is 45%. The frame of the window has a circularity of around 70%, but the glass has a circularity of 20%. So that's why the MCI score, the material circularity index, is lower. Then the deconstruction score is around 80%. And the total disassembly time, I found that very interesting and very useful, because if it takes too long to disassemble a product, that's not economically feasible. It takes 42 minutes. And the limitations include rolled thermal brakes, epoxy, and petroleum-based materials. And it's very important to note that for this time, we have taken into account the end of life of the product. So not if the product is in perfect conditions, but if it's rusty, if it has been used. And for example, a screw could not be taken out. It will take more time to take out with a screwdriver. We have accounted for that, and that's why it's 42 minutes. It would have been 30 otherwise. And the same has been done for the operable window that can open as well. In conclusion, DFD is essential for reducing raw material extraction and CO2 emission, and there is a lack of standardized assembly documentation, and interdisciplinary collaboration is front-loaded, allowing flexibility in inputs for different user groups. This means that this application can be used in different industries, and the fabricators have provided material recovery lists, assembly time, and sequences. The designers have provided the design limitations, the metrics, and the improvement strategies, and the sustainability experts have the circularity scores, the recovery potential, and this WP data. And the future for this application could be integrated with the BIM and digital twin platforms and create of parametric libraries for connection of components and the Internet of Things. And this research shows how disassembly can be embedded in digital AC workflows, enabling selective deconstruction and circular design across the full life cycle of facade systems. And the recommendations are to use mechanical fasteners, avoid reliance on epoxy, and design things for access so that components that are disassembled are in front of you that are not hidden, for example. Even though it would be cooler to hide the screw, it's better to have it in front of you and take it out easily. And then tag and track materials so that each component, when you disassemble it, you know what it is because it has an ID on it, and you don't just lose components and you don't know what piece it is. So thank you. These are the references. And I would like to thank Benjamin Sanchez for the enlightening conversations on design for disassembly. Thank you very much, everyone, for your time.